Now it's time to actually write a rate law. So for this video, I'm going to guide you through the process of using initial concentration tables to write a rate law. So a rate law is just this relationship between the rate of the reaction and the concentration of the reactants. There is no product here, no products in the rate law, only the reactants. So let's just look at a very simple example here. If this was your reaction here, you can see A and B are going to form C and D, and you have coefficients in front of each. The rate law for this reaction would be rate equals K times the concentration of A to a power times the concentration of B to a power. All right, so couple things to note here. First, there's no products here. It's only the reactants that we care about, the concentration of the reactants in our rate law. K is this rate constant. It will change with temperature, and it can show how temperature here affects the rate of the reaction. And then M and N are what we call these orders of the reaction for A and B. Typically, they are small whole numbers, usually like 0, 1, 2, and you have to determine them by experimentation. That's key, all right? We're not just taking the coefficients here and making them these exponents, making them the orders of the reaction. You cannot use the balanced equation to write the rate law. That is something we really need to drive home, right? Just because this coefficient here might be 2 doesn't mean the order here or the exponent that goes with the concentration of A in the rate law is the same thing. You have to determine this by experimentation, all right? So a rate law is going to have this general format. Rate equals K times the concentration of a reactant raised to a power, and if there's another reactant, times the concentration of that reactant raised to a power, and we call those the orders of the reaction. But you have to determine them via experimentation, and you cannot use the balanced equation to write the rate law. Something very important to note here, the rate of the reaction depends on the concentration of your reactants, but the rate constant K doesn't. K is only dependent here upon temperature and the presence of a catalyst. So K can change here if the temperature changes or if there's if a catalyst is present. But the reaction rate is the one that depends on the concentration here, not the rate constant. This rate law will use concentration and rate data. And very important here, if you're doing this for gases, we can use pressure instead of concentration. So don't, get afraid here if you see a gas problem and you see pressure instead of concentration. You just literally plug in the pressure for the concentration instead. All right, so very important to understand here that this rate constant depends on temperature and presence of a catalyst. Let's talk a little bit more about these reaction orders, those exponents here in the rate law. So they just represent the order of the reaction with respect to a certain reactant. But the overall order of the entire reaction would be the sum of those individual orders of the reactants themselves. So if you wanted to know the order of the entire reaction, you'd have to add up the individual reactant orders here. Again, this is based on experimental data, not the balanced equation. So if I have this equation here, all right, and when I actually do an experiment and figure out the rate law for this equation is rate equals K times the concentration of NH4 plus times the concentration of NO2 minus. Now, if you look at this here, you can see that the reaction is 1-to-1 for them, and then when you actually did the experimentation, you found that the orders of each of them were also 1. Their exponents for both of them are both 1. But that was not determined from the balanced equation. That was determined via experimentation. So if you were doing this, you would say that the reaction is second order overall because you have 1 for the NH4 plus, 1 for the NO2 minus. So when you add them up, it's 2. So the reaction overall is second order. And then how you kind of say this is you would say the reaction is first order with respect to NH4 plus, and the reaction is first order with respect to NO2 minus. Again, this was determined via experimentation, not the balance equation. It just so happens that it can come out to be like the balance equation, but you have to determine this via experimentation and don't just use the balanced equation here. So people always ask, what is the point here of these reaction orders? All right. Well, the idea here is that when an order is a greater value, all right. So if you have like 1 or 2, the higher the order, the more the change in concentration of that reactant will affect the rate. Essentially, by changing that concentration, the order is telling you a little bit about how the change in that concentration of that reactant will affect the overall rate here. So if you have a greater order, changing that concentration affects the rate more. And there's 2 ways to determine these orders. Remember, we have to determine this via experimentation, not the balanced equation. So there's 2 ways you do this. You use something called initial concentration tables, which looks something like this. You'd have to be provided this, or you'd have to work through it in lab to figure it out. So that's what we're going to work on in this video, but you can also do this via graphs, which we'll look at in another video here. All right, so today we're going to focus on how we can determine the rate law and these reaction orders using these initial concentration tables. A little bit more about these initial concentration tables before we get into them. They measure the initial rate of the reaction just after time t=0. So just after the beginning of the reaction here, they measure the initial rate. And it's all experimental data. The key is you have to vary the initial concentrations of the reactants here. Remember, we don't care about the products for the actual rate law. So when we're doing these tables, we vary the initial concentrations of the reactants. But at the same time, you still try to keep those concentrations, at least one of them, the same, and then change the other one so that you can make comparisons here. And I'll show you what that looks like here. But once you make these changes, you vary some of these initial concentrations, you determine the initial rate here for those concentrations. And then we just look at this relationship between the rate and the initial concentration to determine the orders of the reactants. So you have to kind of do this a number of times. It's not like you just do it once. You have to be able to compare experiments here or compare data. All right, so that's what these initial concentration tables are going to do. You're going to vary the initial concentrations here of your reactants while keeping one of the reactants the same usually, and you do this a number of times and measure the initial rate. Let's jump in and look at an example here. You can see you're given an equation here for a reaction, and then you're given the data here so you can see how they kind of varied the concentration and then measured the rate of the reaction at those concentrations. So if you notice here, I just want to point out some things. We said that in order to do these tables, you would have to vary the concentrations here and then look at the rate, and that would help you determine these orders of the reaction, those exponents. So if you notice here, we have the initial concentration of NH4 plus here in this column. So for reactions 1 and 2, or experiments 1 and 2, the initial concentration of the NH4 plus is both 0.100 molar. All right, and then we alter the concentration of the NO2 minus in each, and then we measure the initial rate. But then notice here in experiments 2 and 3, we have the concentration here of the NO2 minus initially being the same, and then we vary the concentration of the NH4 plus, and then we look at the rate for each of those. That's important, all right? You do have to keep an initial concentration the same here while changing another for 2 of the experiments. And you'll see why, and we'll see how we do this as we go forward. But that's just something to realize here. So this first part says, write the basic rate law for the reaction. A basic rate law or a general rate law means you just write the overall setup, but you're not necessarily solving for the orders yet. All right, so if you were writing the basic rate law for this reaction, you would write rate equals K. Remember, all rate laws are going to have that basic setup. Rate equals K. And then you're going to times the concentration of each of the reactants raised to a power. Only the reactants here are involved in a rate law. So we have rate equals K times the concentration of NH4 plus, all right, to a power. You could use any letters here. You could use X and Y. I'm going to use M and N again, all right, times the concentration of the other reactant, NO2 minus, raised to a power as well, N. Okay, this is the basic rate law or the general rate law for the reaction. You don't have to actually solve for the orders yet if you're just writing the general rate law here. All right, so now what you want to do is you want to go and determine the values of M and N, your exponents, your orders of the reaction, using this data table. Okay, so how do we go about determining the order here for a particular reactant? So you look where two trials where the concentration is held constant for a particular reactant. That allows you to examine the data for the other reactant. That allows you to determine the order for the other reactant here. All right, so if you notice, we already kind of pointed this out. The concentration of NH4 plus is constant in experiments 1 and 2, so it's both zero point 0.1 molar, and the concentration of the NO2 minus is constant in experiments 2 and 3. So if I look at experiments 1 and 2 here, all right, that means the concentration of NH4 plus is constant. That will allow me to look at the data here for the NO2 minus and to determine the order of the reactant for the NO2 minus. And if I look at experiments 2 and 3, all right, the concentration of the NO2 minus is the same. So that will allow me to determine the order here for the NH4 plus. All right, so you're always looking for where a particular reactant is constant across two experiments so that you can determine the order for the other. So if we're looking at experiments 1 and 2, all right, essentially we can ignore the NH4 plus because the concentrations are both the same. We want to see how does the concentration of the NO2 minus change, all right? So if we look at this, all right, as we go from 1 to 2 here, I always like to kind of think about it that the higher concentration is kind of on top because it gives you nice whole numbers. So essentially, as you go from 1 to 2 here, you have 0.010 for the concentration, but for experiment 1, the concentration of NO2 minus is 0.0050. So the change in concentration essentially was it doubled, okay? And that's what you see taking place here. The change in concentration, it doubled. And we're raising it to the power here of the order, which we're solving for. Again, you could use any letter. You could use M or N, whatever. I used X here. And then you analyze what happens to the rate when that happens. So, okay, again, I try to put the bigger numbers on top to get whole numbers here. But as I go from 1 to 2, notice what happened to the rate here. We have 2.70 times 10 to the minus 7th in experiment 2, but 1.35 times 10 to the minus 7th in experiment 1. All right, so if you divide those, essentially the rate doubled as well. All right, so if you're kind of setting this up, and I do need to show you more about what's actually happening here in terms of the math on the next slide, but this can kind of, if you're just trying to do this like in a multiple choice and you're trying to figure this out quick, this is how you can kind of do it, and you don't really need to show much work. But when you need to show work, I'll show you kind of how that looks on the next slide here. But basically, you always have your change in concentration raised to the power and set it equal to whatever happened to the rate change here. So essentially, the concentration doubled, all right, to the power of x, and that's equal to the rate doubling as well. So if you were solving for x here, x would be equal to 1. Essentially, the order of the reaction with respect to the NO2 minus would be first order here. All right, so again, let's look at what's actually happening here in terms of the math on the next slide. This is basically the math that you're doing here and kind of giving you an idea of the work that you would kind of need to show. And you can kind of simplify this at least a little bit as I'll explain, but basically what you're doing is you're looking at the one that was greater. I always, like I said, I always keep the greater one on top and you're just dividing the two. right? We're essentially writing the rate law for the first experiment, and then you're writing the rate law for the second experiment, and you're just dividing the two and canceling out what's similar here. So if you notice, I have rate 2 over rate 1 because I want to put the greater rate on top. And that would be equal to, well, if you're looking at the rate law for experiment 2, would be whatever K2 is times the concentration of the NH4 plus raised to a power times the concentration of NO2 minus raised to a power. And then same thing on the bottom for rate 1, it's just that it's all using the information from experiment 1. And the key is here, the reason why we were looking for the concentration of one of the reactants to be constant is because then the concentration of the NH4 plus when we're solving cancels out. And we don't have to worry about that. The K's cancel out because we didn't change the temperature here, so they would be exactly the same. So essentially what we have is we have the rates, all right, over each other equal to the concentrations over each other raised to the power. And if you notice, we get exactly what I had written on the previous slide. You get that the rate change was 2 equal to the change in concentration, which we said was it doubled, raised to the power. And when you solve for n here, it comes out to be 1. So essentially, this is the math you're doing. I would say you definitely need to understand what you're doing here because you might need to use this full setup in some what I'll call algebra versions of this, as you'll see. But at the very least, if you had to show work here, I would have the rates over each other, set them equal to the concentrations over each other raised to the power. And then you wouldn't have to necessarily write this out because they're canceling, but I would realize exactly what is taking place here. Essentially, you're writing the rate law for each of the experiments, and you're just canceling out what's constant. And again, you're doing that looking at how the rate changed, comparing it to how the concentration changed, and solving for the exponent or solving for the order here. So the rate of the reaction with respect to the NO2 minus was 1. All right. And again, you got to make sure you're picking experiments in which one of the reactants concentrations is the same so that you can cancel it out. But that's the basic gist of what you're doing here in terms of the math to solve for the order using this initial concentration table. Since we determined the reaction order with respect to the NO2 minus to be 1, now you could plug that into your general rate law. So we know that its rate equals K times the concentration of NH4 plus raised to a power of M. We didn't find that yet, times the concentration of NO2 minus. We determined that the reaction order with respect to the NO2 minus is 1, so you don't have to write a number there. All right, so now you would need to go and determine here the reaction order with respect to the NH4 plus kind of in a similar way, making sure that you're using experiments in which the concentration of the NO2 minus would be the same. So that would cancel out and allow you to find the concentration of the NH4 plus change here and the rate change to determine the order. So I already pointed out earlier that in experiments 2 and 3, the concentration of the NO2 minus is the same. So that'll allow us to focus on here the concentration of the NH4 plus, seeing how that changes, seeing how the rate changes, and then determining the order here. Remember, you should be aware of the math here. Essentially, you try to put the bigger one on top. So it looks like the concentration and the rate is greater for experiment 3. So I would do rate of the third one equals the concentration of your NH4 plus raised to a power all over the rate of the second one equal to the concentration of your NH4 plus there raised to the power. All right. And again, the K's would cancel because you're not changing the temperature and because you're picking experiments in which the concentration of NO2 minus are the same, they would cancel as well. So when you set this up, your rates here, when you divide those, you get 2. And when you divide the concentrations, you get 2 as well. Essentially, they both doubled. So when you solve for the order here, the reaction is going to be first order with respect to the NH4 plus, the same as it was for the NO2 minus. They don't have to be the same, but in this case, they came out to be the same. And again, you should be aware of how to set this up with the math. I'm just kind of showing you the quick way here, but now you determine the order for your other reactant here from this data. Now we can write the actual rate law here. So we'd say rate equals K times the concentration of NH4 plus times the concentration of NO2 minus. All right, so each of the reactants is first order. So when you combine that, the reaction is second order overall. All right, so this would be the actual rate law for this particular reaction. Remember, we didn't use the balanced equation. We used the data here to determine the orders. All right, that's very important here. So you need to be familiar with the basic setup of the rate law, how to determine the orders, definitely understanding that you cannot just write this from the balanced equation here, knowing that K is the rate constant and it is impacted by temperature and the presence of a catalyst here. All right, so you definitely need to be able to do this using the data. Typically here, once you determine the rate law for the reaction, you might be asked to determine the rate constant now. Now, once you know the official orders here of the reaction, you can determine the rate constant. All you do is pick any experiment and just plug in to your rate law. All right, so you basically just pick one of the experiments and plug in. So I picked experiment 1 here. So the rate for experiment 1 is 1.35 times 10 to the minus 7 molar per second. Uh, K is what I'm solving for, and it's going to be equal to the concentration, K times the concentration here of each reactant, and they're both to the power of 1 because the order for each was 1. So you just plug in the concentration from experiment 1. Be careful. Make sure you're using the concentration data from experiment 1, and then you just do the math and solve here. The key is you just have to be careful with your unit for K. All right, that's very important. You have molar times molar here, so that would be molar squared. And then in order to solve for K, you would divide that by both sides. So essentially you have molar per second divided by molar squared. All right, when you actually do the math and see what's going on here, you get molar to the -1 seconds to the -1. All right, sometimes it's helpful to actually look at the math here and think about it. But we had molar per second divided by molar squared, which would be the same thing as timesing by 1 over molar squared. All right, so when you do your canceling here, molar cancels on top with one of the ones on the bottom. So the only thing you have left for your units is essentially 1 over molar times seconds, which is the same thing as molar to the -1 times seconds to the -1. So you really got to be careful with your units here for K. You have to watch, but that's kind of the hardest part here. Just once you have your rate law, pick one of the experiments, plug in, solve for K, watch your units. What if you get a problem and you don't have the concentrations being constant for a particular reactant? Well, then you have to use algebra here. And again, if you paid attention to the math setup I showed earlier, this will actually make complete sense. So if we look at this example, we have a pretty basic reaction here, A plus B going to 2C. We have our initial concentration table here. If you notice, the concentration of B is constant in reactions 1 and 2 here. All right, so the concentration of B is the same in both of those. So that makes A easy to determine. You can determine the order of the reaction with respect to A easily. But if you notice here, when you're looking at the concentration of A, it's never constant. All right, so that makes determining the order here for B a little bit more interesting. All right, so let's knock out the order here for A right now. All right, so if B is the same here in experiments 1 and 2, look at what happens to the concentration and the rate for A in experiments 1 and 2. So if you notice, all right, again, I try to keep the bigger numbers on top here. The rate quadrupled here. So 4.8 divided by 1.2 is 4. And that would be equal to what happened to the concentration change. 1 divided by 0.5 is 2. So 2 to the power of x equals 4. When you solve for x, all right, you found out here that the reaction is second order with respect to A. All right, so you determine now the order of the reaction with respect to A, but now we have to do this for B. Again, B is kind of interesting because the concentration of A is never constant here. So you're going to have to do a little bit more work, but it's just showing your work, doing the algebra, and you can quickly determine that. But the key is if you have a reactant that doesn't have the concentrations of the other one being the same. So for example, here we're trying to find B, so we need A to be the same, and it's not. You would want to find the order of the reaction for the other one first. All right. So notice here, A is never the same. So we determine we determine the order of the reaction with respect to A first. And now we'll work on B when A doesn't have any being the same here. So that's important. All right. If you have one that doesn't have any of the concentrations that are the same, work on the other order first. You're doing exactly what you did before. The only difference is the math is a little bit more interesting. So you just have to pick two experiments here and then plug in what you know. All right. Again, we already determined the order of the reaction with respect to A. So now we're working on determining the order of the reaction with respect to B here. So I picked experiments 3 and 1. All right, because that was the experiment here in which B was not the same. All right, if you're going to do this, you want to make sure here that essentially B doesn't cancel out. All right, so you have to pick experiments that doesn't allow the one you're doing here to cancel. All right, that's important here. So essentially, it's the same thing. You're doing rate 3 over rate 1, again, the bigger one on top, equal to your K3 concentration of A in the third one, but this time A is raised to the power of 2 because you determined his order, times the concentration of B in this one to the power that we need to determine. All over all the same data, but now for experiment 1. And again, A is still raised to the power of 2 because you determined that order. So when you plug everything in here, like I said, the math is just a little bit more interesting. The K's cancel because they are the same as long as you don't change the temperature here. You don't change the K, so they're gone. But the only difference here is we don't get rid of one of the concentrations because we didn't have a case of when A was the same. So we have essentially both concentrations here, and we have to just do the math here to solve this. All right, so just be careful here with the math. That's all you need to do is be careful with the math here. Essentially what happens is when you do the math here, when you divide the rates, this comes out to be 32, all right? And that would be equal to, when you do the math here, 2 squared is 4, divided by 0.5 squared, which is 0.25. So you have 4 divided by 0.25 is 16, all right? So if you need to see this written, essentially what you have is when you divide the rates, you have 32 equal to 16 when you do the math of 2 squared divided by 0.5 squared, all right, times, well, 1 divided by 0.5 is 2, all right, to the power here of m, all right? So you're just solving for your exponent here. All right, well, again, if you did the math, you'd be at 32 equals 32m. So if you did the math, solve for the exponent, m is going to be equal to 1. So the reaction is going to be first order here with respect to B. All right, so again, you pretty much know how to do this. It's just that when you don't have the concentrations being constant for a particular reactant, it just makes solving for the other one a little bit more interesting. But if you understand what you're actually doing here to find the orders, and you can do math, it pretty much isn't that bad. You just have to remember to find the order of the other one first, and then you have to work on the one where you can't find any of the concentrations being constant. So now if I write the overall rate law here for this reaction, it would be rate equals K times the concentration of A squared times the concentration of B. Okay, so that would be the overall rate law here determined via experimentation using the data. The reaction would be second order with respect to A. The reaction would be first order with respect to B. And then the reaction order overall would be third order when you add them up. A little bit more here for you to think about with these reaction orders. Remember, the higher the number here, the greater the change in concentration of that reactant impacts the rate. So if a particular reactant is zero order, essentially what that means is a change in concentration has no effect on the rate here. All right. So for example, if we're looking at this right here, if you got math like this, essentially you doubled the concentration, all right, but then the rate stayed exactly the same. It didn't change. When you solve for your exponent here, it would be zero. Essentially, that reactant is zero order. Changing the concentration of that reactant has no impact on the rate. So if you were writing the rate law here with one reactant, your rate law would just be rate equals K. There's no reactant at all because that particular reactant was zero order. You can have a reactant being zero and you wouldn't write it in the rate law. If you had another reactant there and it wasn't zero order, you would include that then. All right, so that's something you got to be aware of. If something is zero order, changing the concentration has no effect on the rate. If something is first order, when you double the concentration, then you double the rate. All right, so that would be exactly proportional here. So if we doubled the concentration, the rate doubled as well. So when you solve for your exponent, it would be 1 or first order. If you had just one reactant, it'd be rate equals K times the concentration of A. If a reaction is second order, basically what that means is when you doubled the concentration, the rate quadrupled. Or if you tripled the concentration, the rate increased by a factor of 9, and so on. Okay, so essentially here, if you were looking at the math, if you doubled the concentration, raised to your power here, your exponent, your order, the rate change was quadrupled. If you solve for x, it would be 2. Same thing, if you tripled the concentration uh, and the rate went up by a factor of 9, you solve for x, it would be 2 as well, second order here. So it's very important to understand how the changes here in the concentration affect the rate for each of these orders. And if you were writing the rate law for second order, depending on your reactants, could be rate equals K times concentration of A squared, so on here. All right, so pay attention. This is a big idea that you need to understand. What happens here to the rate if you change the concentration, you have a particular order. So definitely make sure you understand the ideas on this slide. So just want to point out here the reaction orders and the units of K. For example, if you had a zero order reaction and you had rate equals K, your K units must match the rate units. As long as your rate units were in molar per second, your K units would be exactly the same thing. If you had a first order reaction, your K units are going to be in seconds to the -1. Because think about this, if rate is in molar per second and the concentration is in molar, your K must be in per second, all right, in order to make the rate units work. If your reaction is second order, the K units would be molar to the -1 times seconds to the -1. And if your reaction is third order, your units for K would be molar to the -2, seconds to the -1. And you can pretty much see how this goes. Essentially, if the reaction was fourth order, it'd be molar to the -3, seconds to the -1. Uh, Basically here, aside from zero order is molar per second, you basically just get, depending on your overall order of the reaction, it's just one less for the molarity here. All right, you're always going to have molar to the negative something times seconds to the negative something, but seconds to the -1, sorry, but it's always one less for the molarity than the order. So if you have second order, one less for the molarity is going to be molar to the -1, seconds to the -1. Third order, one less for the molarity, so molar to -2, seconds to the -1. Um, you don't have to memorize these. You could use that little trick I just showed you. But if you just look at the actual math you're doing when you're solving for K, you can pay attention to the units and see what the actual units would be. All right. So again, if you just pay attention to the math, you can see what's canceling and what the overall units would be. But you got to watch your units on K. That is something that's important and counts. And AP is very specific here about making sure you get those units correct. So there's a couple ways you can kind of think about it. You can kind of use the little trick. You can use the math to see what it is. But you definitely need to be careful with the units of K. Let's jump in and do an example. You can see here that we have the initial concentration table. The problem says the initial rate of the reaction for A plus B going to C was measured for several different concentrations as shown above. Using these data, determine first the rate law for the reaction. Then we have to do the rate constant, and then we have to do the rate of the reaction under kind of new conditions here, when the concentration of A is 0.050 molar and the concentration of B is 0.100 molar. All right, so we're going to work through this. We'll start by doing the rate law of the reaction by determining the orders here. All right, so I'm going to start by writing the general rate law, just so I have a frame of reference here. For the reaction, it would be rate equals K times the concentration of A raised to a power, I'm going to use X this time, times the concentration of B raised to a power, I'm going to use Y. All right, so that's the general rate law here. So now what I need to do is I need to actually go through and find the orders. So the first thing I notice is in experiments 1 and 2, the concentration of A is constant. All right, so that means I can figure out the order of the reaction for B using experiments 1 and 2. So I noticed that the concentration of B is higher in experiment 2. I always want the higher ones on top. So if I was doing this, it'd be essentially rate 2 info over rate 1 info. I'm going to write it out so you can see it here because I think it's important to know what's actually happening. So we have rate 2 over rate 1, and that would be equal to K2 times the concentration here of A2 raised to the power of X times the concentration of B2 raised to the power of Y, all over K1 times the concentration of A1 to the power of X times the concentration of B1, all to the power of Y. Okay, so before I even plug anything in, all right, I know that I'm not changing the temperatures, so K is going to cancel. In experiments 1 and 2, the concentration of A is the same, so that's going to cancel. So when I just plug in the information that's left, the rate info and the concentration info for B, I get 4.0 times 10 to the minus fifth, all over 4.0 times 10 to the minus fifth, equal to the concentration. Be careful here, 2 is on top, so the concentration of 0.200 to the power of Y, all over 0.100 to the power of Y. All right, so essentially what I get here is when you divide the rate data, you get 1 equal to 2 to the power of Y. Essentially what happens is when I doubled the concentration, the rate stayed the same. All right, so when you solve this for Y is equal to 0. So essentially here, what that means is that the reaction is 0 order with respect to B. All right, but I still have to now determine the order here with respect to A. So I look at the table and I see in experiments 3 and 1, the concentration of B is the same. So that'll allow me to determine the order here for reaction or for reactant A. So I notice that the concentration of A is greater in reaction 3. So essentially it's going to be rate 3 info over rate 1 info. So again here, I'll just do this so you have a good idea again for this first one of what you're actually doing, but you're doing rate 3 all over rate 1 info. So essentially it's K3 times the concentration here of A3 to the power of X times the concentration of B3 to the power of Y. Now, we already did determine this info for B, but remember here, it's going to be constant. It's going to cancel out anyway, so it doesn't necessarily matter. All over K1 times the concentration of A1 to the power of X times the concentration of B1 to the power of Y. So again, when you cancel this out, your Ks are going to be the same because you didn't change the temperature. In reactions 3 and 1, the concentration of B was the same, so B cancels. So it's just the rate 3 over rate 1 equals concentration of A3 over concentration of A1. So if you were doing this now that you got the hang of this, you know what you're doing. This is not an algebra one. You could just show me kind of what I'm writing over here. This would be enough math to show your work here for this. If you have to show your work, you don't need to show all the canceling, but understanding what's actually happening is very important, especially for those algebra problems. So essentially, when I grab the information here, I got 16.0 times 10 to the minus fifth all over 4.0 times 10 to the minus fifth equal to, remember, you have 3 over 1, so you need the concentration for A from experiment 3 over 1, should be 0.200 to the power of X all over 0.100 to the power of X. So essentially here, when you do your math, you get 4 equal to 2 to the power of X. Essentially, when you doubled the concentration, the rate quadrupled. So when you solve for X, X equals 2. So the reaction is second order with respect to A. All right, so now you can write the overall rate law here. What you wrote at the top was just your general rate law or your basic rate law. Now we can write the actual rate law based on our experimentation determining the orders here. So it would be rate equals K times the concentration of A squared. And then because the order of the reaction for B was 0, it doesn't even participate in the actual rate law. So this would be the rate law here for that particular reaction. If we keep going in this problem, the next part of the problem wants us to solve for the rate constant. So we already know here the actual rate law. We just determined that in the previous part. So that was rate equals K times the concentration of A squared. So you just pick one of the experiments and plug in to your rate law and solve for K. Just watch your units. I'm going to pick experiment number 1. So when I plug in, I have 4.0 times 10 to the minus fifth molar per second. Pay attention to your units here. Equal to K times the concentration of A in experiment 1, which is 0.100 molar, and it's squared. All right, so now you're just going to solve for K here, but watch your units. When you do your math, you get 4.0 times 10 to the minus third. Essentially, you have molar per second divided by molar squared. If you use the little one less trick, the reaction here is second order overall. So you would expect the negative on the molarity in your K units to be 1 less than that. So essentially, you would expect it to be molar to the negative 1 times seconds to the negative 1, all right, using the little trick. If you look at the math, it comes out to be the same thing. Molar per second divided by molar squared, it comes out to be 1 over molar times seconds, which is the same thing as molar to the negative 1, seconds to the negative 1. So you either need to use the trick or you need to be able to look at the math here. The key is you need to pay attention to those units with K and you need to get them correct. All right, so essentially that takes care of the rate constant. That was part B in the problem. If we look at part C now, part C wants us to determine the rate of the reaction when we have the concentrations here being different. Okay, so they gave us concentration data. They said that, well, what happens if the concentration of A is equal to 0.050 molar, and the concentration of B was equal to 0.100 molar. All right. So we just need to take this information, plug it into our rate law, but now we know the value of K. All right. So when we plug this in, we know that rate is going to be equal to K, which we found to be 4.0 times 10 to the minus third molar to the negative 1, seconds to the negative 1, times the concentration of A squared. All right. So when we plug in the concentration of A, it's going to be 0.050 molar, and that's going to be squared here. All right. Notice the concentration of B didn't even matter because B doesn't have an impact here in our rate law because it's zero order. All right. So when you solve for the rate here, just do your math. Don't forget to square the concentration of A. When you do this and solve for the rate, with correct sig figs, should come out to be 1.0 times 10 to the minus fifth molar per second. All right. Again, if you actually watch your units here, you would have molar to the negative 1 second to the negative 1 times molar squared, and your units do come out to be molar per second. So pay attention to that. That's what we would expect the units to be for the rate, though. All right. So this is a very typical problem where you would have to use the table to find the orders, then pick an experiment to find for K, and then use K and information to maybe find the rate here. All right. So definitely need to be able to do this using the initial concentration tables. For the next example here, we are given our initial concentration data table. This one has 4 experiments though, and if you notice, there are 3 reactants in the reaction, so that makes it a little bit more interesting, but the steps basically are exactly the same. So the reaction is given, and then it says using this data given, we got to determine the rate law, the overall order of the reaction, and then the rate constant. Okay, so in order to determine the rate law, I'm going to look where concentrations are the same, but this time, in order to determine the order for a particular reactant, I need to make sure the other 2 reactants are constant, all right, because there's 3 total reactants here. So you just got to be careful with this, but the overall process is exactly the same. So that's what we're going to do first. To write the rate law, we're going to need to determine the orders here for each reactant. Okay, so let's jump in and actually solve for the orders here of these reactants. The first thing I'm going to do is I want to write a general rate law. So I know it's going to be rate equals K times the concentration of the first reactant, BrO3 minus, to a power, I'm going to use X, times the concentration of Br minus, to a power, I'm going to pick Y, times the concentration of the other reactant, H plus, to a power, I'm going to use Z here. All right, so I'm going to start with the BrO3 minus. Very important to keep this organized. Pay attention to what you're doing. There are 3 reactants here. So I notice immediately here, though, when I want to do the order for BrO3 minus, in experiments 1 and 2, the concentration data for the Br minus and the H plus are both the same for each, so they would cancel out. So that means I can use experiments 2 and 1 here to determine the order for the BrO3 minus. I see the concentration is greater in experiment 2, so I'm essentially going to do experiment 2 info divided by experiment 1 info, and I'm only going to show the rate and the concentration data here. So the rate for experiment 2 is 1.6 times 10 to the minus third, all over the rate for experiment 1, which is 8.0 times 10 to the minus fourth, equal to the concentration here for experiment 2 for the BrO3 minus, which is 0.2 to the power of X, all over 0.1 to the power of X. All right, so essentially here, when I do the math, I get 2 equal to 2 to the power of X. So essentially when I doubled the rate, the concentration doubled, so that's going to be X equal to 1. So the reaction is going to be first order with respect to the BrO3 minus. Okay, so now I'm ready to work on the Br minus. For this one, again, we have to make sure the other two are constant here. I notice that in experiments 3 and 2, all right, if you notice, the concentration of the Br minus changes, but the BrO3 minus is the same in both, and the concentration of H plus is the same in both. And it's the Br minus is greater concentration in experiment 3, so essentially I'm doing 3 over 2. And again, I'm just showing the rate and the concentration data here. So I have 3.2 times 10 to the minus third all over 1.6 times 10 to the minus third from experiment 2, equal to the concentration data. I got 0.2 to the power of y all over 0.1 to the power of y. So again, when I do my math here, I get 2 equal 2 to the power of y. Essentially, when I doubled the concentration, all right, doubled that concentration, the rate doubled. So when you solve this for y, y is going to come out to be 1. So the reaction is first order with respect to the Br minus. But I still have one more reactant to go here. Now I have the H plus. Again, though, you have to figure out where the other two are constant, but the concentration of the H plus is actually changing here. All right, so it looks like the concentration of the other two are going to be constant in experiments 1 and 4. If you notice in 1 and 4, the BrO3 minus is the same. Same thing for the Br minus, but the concentration of the H plus doubles here. All right, so you're just going to plug in. Essentially, it's going to be greater in experiment 4 for the concentration of H plus. So you're going to do 4 over 1. So when I do this here, I get the rate being 3.2 times 10 to the minus third in experiment 4, all over the rate in experiment 1 being 8.0 times 10 to the minus fourth, equal to concentration from 4 over 1 should be 0.2 to the power of z, all over 0.1 to the power of z. So when I do the math here, I get 4 equal 2 to the power of z. So essentially, when I doubled the concentration, the rate quadrupled. So when I solve for the exponent, z is equal to 2. So the reaction is second order with respect to the H plus. So now I can write my overall rate law, plugging in my orders. So I have rate equals K times the concentration of BrO3 minus, all right, it's just 1, times the concentration of Br minus, it's also just 1, times the concentration of H plus squared, all right? So that takes care of the rate law here. The second part does ask for the overall order of the reaction. So 1 plus 1 plus 2 is 4. So the reaction is fourth order overall, okay? So that takes care of the rate and the overall order of the entire reaction here. But then the last part of the problem wants us to determine the value of K here. In order to determine the value of K, you just pick one of the experiments and plug in all the data. Again, I'm going to pick experiment 1. Typically, I always pick experiment 1. So I'm going to plug in the rate data. It's 8.0 times 10 to the minus fourth. Again, pay attention to your units here. Molar per second. We're solving for K. Concentration of BrO3 minus is 0.1 molar times concentration of Br minus, 0.1 molar times concentration of H plus, which is 0.1 molar, but it's got to be squared. All right, so you're just going to solve for K here. Watch your sig figs. So when you plug and chug this, you get 8.0. Now your units here, again, you could pay attention to the math. You're doing molar per second divided by, when you solve for K, it'd be molar to the fourth. All right. So again, if you use the little trick here for this, remember the reaction order overall is fourth order. So you would expect your molarity to be to the negative of 1 less than that. So your units would be molarity to the negative third. seconds to the -1, as always. All right, so you can look at the math. The math gives you the exact same units, but the little trick also gives you those units. All right, so again, this was just another example here, being able to determine the orders, being able to determine K, writing the rate law, making sure you can use these initial concentration tables and then do the math.